Hello, welcome to this session discussing data-centric innovation. My name's Robert Merlicek, and I'm the APJ CTO for TIBCO. I also have with me in this session, Wenyan, Principal Solution Architect from the Office of the CTO US, and Alan Lee, Solution Architect from the Office of the CTO in APJ. There has been a monumental shift in the information landscape that I call the rise of data. You could attribute this to the adoption of smartphones, sensors, and connected vehicles and appliances, among other digital artifacts. Much of what we touch and work with now automatically generates data, but the real reason why we're seeing this increase is the growing use of data analytics and automated systems. The past decade's data explosion created a continuous cycle of data analysis and actions, leading to new insights, data creation, and more data analysis. We've seen companies collect more data than ever before as they've raced to transform their businesses and make data-driven decisions. According to IDC and Seagate Data Age report, the global datasphere will grow from 33 zettabytes in 2018 to 175 zettabytes in 2025. By 2025, almost half of all data worldwide will reside in public cloud, and 30% of all data will need real-time processing as the role of the edge continues to grow. We have seen an evolution of data, and some of the traditional ways we look at data needs to be reevaluated. The challenge is we now live in a connected world where IoT, cloud, and big data movement has resulted in much more data being collected at much higher rates. Many of these data structures are no longer consistent as they are changing with the data. And in particular, the information now is related, dynamic, and constantly evolving. So we need to rethink how we deal with the new data velocity, variety, and distribution. So this gives rise to new challenges of identifying relationships and patterns in data so that we can understand the information at a much deeper level. A challenge now is not just to see the data, but understanding the relationships. Like a floating iceberg, so much of it can be hidden. So the deeper the understanding of the relationships, the more powerful the insights. And with enough relationship data points, you can even make predictions about future events and actions. But as more data is connected and the size and complexity of the connected data increases, the relationships therefore become more complicated to store and query. One of the responses is, why not just use traditional data structures and technology? Well, relational models struggle with highly connected dynamic data. They require the use of predefined schemas and join tables. It's difficult and expensive to model n degrees of separation. And SQL joins in queries can become very complex. So this evolving data needs to move past fixed schemas, as we need to be able to model new relationships in this dynamic data. Another factor is that as the data sets dramatically increase in size, we see significant performance impacts with traditional relational databases. Since the traditional ways are no longer good enough, we need a new and innovative way to represent and analyze data. We need more flexible ways to answer questions with dynamic data structures to support business digital transformations. Discover and identify complex patterns from the highly connected and distributed data. We need the ability to store and represent complex data relationships with constant query performance, which is especially important as the data sets grow. The ability to apply advanced analytics and AI while preserving the data privacy and confidentiality over the data set. And especially important in real-time systems is that data and events can be processed as quickly as they are generated. So graph technology addresses many of these previous shortcomings, so we can look at the data differently. Graph databases transform a complex web of dynamic data into meaningful and understandable relationships. They allow us to stream analytics and contextual data in real time, facilitate efficient entity link analysis, which is triggered by event arrival, leverage connected data during that stream processing, and eliminate complex joins and self-joins in a traditional relationship model. Because of these new requirements, we are looking for a new data representation that augments traditional relational databases. These relational databases are more well suited to understanding data structures that don't change too frequently and known problems involving discrete parts of data or minimal connectivity. Whereas graph databases are really well suited to these dynamic systems where the data topology is difficult to predict, dynamic requirements that data structures evolve with the business. They're good to answer unanticipated questions, easy to model and store those data relationships, and they are really, really fast to query across records and very large data sets. Many companies now use graph technology to deal with their extremely large data sets and high velocity and variety of information. Some of these include Amazon, Google, Facebook, eBay, Instagram, and Twitter, to name just a few. For a graph, think of the elements as nodes or dots. Each node has a key value, pairs, and a label. Nodes are connected by relationships or edges. Relationships have a type and a direction, so they can have properties. A graph database is simply composed of dots and lines. This type of database is simpler and more powerful when meaning is in the relationships between the data. Relational databases can easily handle direct relationships, but indirect relationships are more difficult to deal with. When building a relational database, it is built with questions in mind. What kinds of questions we will be wanting to answer? For example, do you want to know how many people bought a toaster or live in Kansas, have a criminal record, or use a coupon to buy that toaster? If the database administrator or the person who created that database did not anticipate some of these questions, it may be very difficult to receive the right information from that relational database. For graph databases, it's possible to answer unanticipated questions. With a graph, you can answer any question as long as the data exists and there is a path between them. A graph is designed to traverse indirect relationships. With the graph databases, you can even add more relationships and still maintain performance. A graph database stores data relationships rather than the data points. TIBCO Labs has built a new project that uses graph technology at its core called Project Journey. Project Journey manages data in new and innovative ways using graph technology to create a highly personalized real-time experience, which can be applied for operational optimization, track and trace, sentiment analysis, and customer interactions, to name a few. It leverages TIBCO Graph Database, which is AI-driven and cloud-native. It leverages large real-time data sets and relationships between data to predict, measure, recommend, analyze, and take predictive action seamlessly. And we've seen application areas like customer journey, crime journey, transport journey, emergency management journey, and healthcare journey, to name just a few. As we see from this high-level architecture diagram, Project Journey leverages TIBCO Graph Database to store the data. We communicate with TIBCO Cloud Messaging and open APIs. TIBCO Cloud Integration manages the real-time integration and automation with TIBCO Cloud events. And analytics, visualization, and machine learning is seamlessly carried out with TIBCO Spotfire and Spotfire mods. In the next session, we will dig down into the architecture in more detail. Now let's hear from Wenyan about how we can leverage federated learning in data innovation.
So as Robert has presented, the data is highly connected, but at the same time, it is also highly distributed, resides on devices and servers owned by different individuals or companies. So imagine if we could bring this data together, we could gain insights, detect problems, and create solutions we won't be able to do, or at least more efficiently and accurately with siloed data, such as fraud detection in financial and insurance industries, medicine research, disease detection, supply chain improvement, etc. However, data ownership and data privacy and confidentiality make data sharing very difficult, if not impossible. So how do we overcome these difficulties? Today, we'll explore some of the techniques. First is federated learning. So let's take a look how it works. In federated learning is a machine learning technique. Instead of bringing data to the model is pushed to devices where the data is located. The model is trained locally. The trained weights and parameters are sent back to a component called aggregator to be combined and feedback to local model again to be further trained. The process iterates until a certain accuracy is achieved. The data never leaves the local device. Another technique is called synthetic data generation. Synthetic data is generated from real data through 3 steps: learn, generate, and evaluate. During learning phase, statistical or machine learning models are applied to the original data. Then sample data is generated. And finally, the synthetic data is evaluated again against the original data to generate data utility and data privacy reports. The synthetic data should be as close to the original data as possible while preserving data privacy. The steps can be iterated until the synthesized data meets your needs. So now let's take a look at what we're doing at TIBCO Lab on these 2 techniques. TIBCO Federated Learning supports Intel OpenFL framework. It runs in the cloud, provides a UI to facilitate collaborators such as data scientists and data providers to come together to form a federation. Once a federation is formed, data scientists can upload models to be trained, create training plans, and schedule training tasks. Once the jobs are completed, data scientists can view the job report and download trained model. Data providers' task is quite simple. All it needs to do is configure the training data location through the UI. Only this collaborator agent needs to run on a local machine where the data is located. The agent will monitor and pull down training tasks to run locally. TIBCO provides a aggregator components process to coordinate the training and aggregate training parameters. The typical synthetic data projects follow the same architecture approach as federated learning. Data providers can use the UI to define metadata about the original data, specific data constraints and privacy requirements, and configure synthetic tasks from a UI. Same as federated learning, a local run agent will monitor and run submitted tasks on device where the original data is located. Once tasks are completed, evaluation matrix and graphs are uploaded into the cloud. And so Currently, we support 2 libraries. One is from MIT Synthetic Data Vault, and another one is Microsoft OpenDP Smart Noise project. So this is a very high level overview of what we're doing. So if you are interested and want to know more details, please visit TIBCO Lab. So now I'm going to hand it back to Robert.
Thanks, Wenyan. So in summary, we have seen that new techniques and architectures are required to understand complex data relationships. Graph technology is one of the next major evolutionary steps to help enhance data and analytics. At TIBCO, we have adopted open architectures, cloud-native deployments, and AI and ML-driven capabilities, core characteristics. And lastly, federated learning and synthetic data are 2 of the techniques to allow data to be shared while preserving data privacy and confidentiality, and will be a big focus in the future. And with that, I'd like to thank you for joining us today.